nanohub.org.
Online simulation and more for nanotechnology.
And this week for atomic force microscopy, and well, the title of the presentation is Fabrication and Characterization of Nanostructure using AFM. Today our presenters will be Dr. Wesley Sanders. You can see Wes here in the Zoom. He's an assistant professor at Salt Lake Community College, and also we will also have Glen. Oh my gosh! I use this. This is Glen Johnson, not Rich Hill. I just saw that. That's a cut and paste thing. He is the. Oh man, is that what I had? Microscopy lab coordinator. Do I have the title right? Yeah, microscopy lab coordinator. And that's his real actually official title there, or email there. And that is a picture of Glen. We had to search far and wide for a picture of Glen, and we got a picture of him. We've been working with Wes and Glen for years and years, and they're fabulous folks and fabulous partners. And I think you're going to find the next couple of hours very worthwhile for you. So without further ado, I want to turn this over to Wes, who's going to be leading off. And actually, I think Glen is going to be kind of batting cleanup at the end of the session, doing the demo. So I'm going to stop my sharing and turn it over to Dr. Wesley Sanders from Salt Lake Community College. And thanks, Wes, and thanks for your work on this.
Hey, no problem, Bob. Thank you for the introduction. So I'm going to share my screen with everybody, and I have a few embedded in this presentation to just to kind of give you a visual regarding the types of fabrication and characterization procedures I'm going to be talking about in this presentation. So if you have any problems hearing any of the animations or viewing them, just mute yourself and let me know, or just let me know in the chat. So can everybody see my screen okay? Yeah, we're good. Okay, excellent. All right, wonderful. So what we're going to discuss today is we're going to look at a series of fabrication techniques, nano and micro fabrication techniques involving atomic force microscopy. Now, oftentimes it's necessary to use some very specialized imaging techniques in order to see the structures that are printed using this atomic force microscope. Now, the atomic force microscope is just one flavor of scanning probe microscopy. Scanning probe microscopy, or SPM, is an umbrella term. So scanning probe microscopy involves the use of a specialized probe in order to sense a signal on the surface of a substrate for the purpose of characterizing nanoscale and microscale structures. Now, just a really quick bit about my background. I earned a PhD from Virginia Tech, and I earned a PhD at Virginia Tech back in 2008. And while I was working as a graduate student at Virginia Tech, I was introduced to my first type of scanning probe microscope, which was the scanning electrochemical microscope, or the SECM. Now, in that particular case, the SECM involves the use of a very small platinum tip embedded in a glass capillary. And in that case, you use the ultra micro electrode, it's called, to scan sample surfaces using redox current, because this was a technique that was performed in an electrolyte. But it wasn't until my postdoctoral work at the Naval Research Lab, it was then where I learned how to use the atomic force microscope, which again is one of many flavors of SPM, or scanning probe microscopy. So what I want to do first is I want to give you an overview of the types of AFM lithography processes we're going to talk about today. We're going to talk about nanoshaving. We're going to talk about nanografting, which involves a nanoshaving step. We're going to discuss dip pen nanolithography, or DPN for short. We're going to discuss thermal DPN, which is a flavor of DPN. Electrochemical DPN is another flavor of DPN nanolithography. And I'm gonna give you an overview of anodization lithography, which involves using about 10 to 20 volts under ambient conditions in order to oxidize surfaces directly under the AFM tip, okay? Now, the purpose of this talk is not to give you an exhaustive overview of each of these topics. I just want to provide you with enough information so that you have a basic understanding of how it works, what you can use it for. And at the bottom of each slide, I've included some references from the literature that you can consult if you want additional information regarding this any of these techniques. So before I get to the specifics regarding nanofabrication, I just want to give you just a quick and dirty overview of how the AFM works. So the AFM's primary role is to record surface topography. And in order to do so, there's some key components that the AFM uses. So we have our probe, which is a inclusive term that involves the chip. That's how we mount the probe into the AFM scanner. We have a cantilever or flexing diving board whose role is simply to bend as the tip traces the sample surface, okay? So an analogy that I saw several years ago that is used to describe AFM operation, it's like using Braille. I think that's a really nice analogy. So you use your finger to trace over the Braille text. And basically every letter or character has a specific pattern associated with it. And that's exactly how the AFM works. We have a tip mounted on a cantilever, and the tip simply traces the sample topography. Now the tip has nanoscale dimensions, right? So we can't see using ordinary optical means, we can't see the movement of the tip as it traces the sample surface. So we have an elaborate setup of electronics that are used to trace or to monitor tip sample interactions. So we have a laser beam that's aimed at the back of the cantilever, and the cantilever is coated with a reflective material that allows the laser beam to be reflected and directed to a 4-quadrant photodetector that generates an analog voltage that's proportional to the tip motion. And then we have a feedback loop, a series of feedback loop electronics that's used to convert the analog signal from the photodetector to a digital signal that the computer can then use to map your surface topography. Now, we'll mention the feedback loop a little later because that has direct relevance to one of the specialized imaging techniques we want to talk about a little bit later. So this is a scanning electron microscope image of an actual AFM tip. So you can have some idea of what's actually patterning the surface and subsequently imaging the surface as well. So we have a pyramid-shaped tip mounted at the end of our flexible cantilever, okay? So the apex of our pyramid-shaped tip is about tens of nanometers in size. So the small size of the tip allows us to easily manipulate atoms and molecules on the surface of our substrate. Now, even higher resolution can be achieved in AFM lithography if we use an even smaller tip. Okay, I want to point out that normal fabrication processes such as photolithography and etch, the same processes that are used in the semiconductor industry, those are used to machine the AFM probes. But additionally, you can make the probe smaller by using reactive ion etch or focus ion beam milling to make the tip even sharper to produce higher resolution or skinnier lines as you print your structures on your substrates. So before I get into the different types of lithography that I mentioned before, I want to briefly talk about self-assembled monolayers or SAMs. Now, the reason I want to give you a brief overview of SAMs is because they're oftentimes used as a template or the film that's etched with the AFM tip. So a self-assembled monolayer is basically a well-ordered molecular film that's assembled on gold or silver substrates, okay? Now, an alkane thiol molecule consists of a sulfur atom, a carbon chain, and a functional group at the other terminal end of the molecule. Now, the sulfur atom attaches to the gold or silver substrate, and the long carbon chains are responsible for organizing the film. Now, all the magic happens with the head group or the functional group that's at the top of our resultant molecular film. Now, what's nice about these functional groups is they can be tailored or modified to meet our needs. So for instance, if you're a biologist and you want to create a film that's going to support biological adhesion, then you can use an alkane thiol with the appropriate head group that will allow the cell body to actually stick to the film. If you want to take advantage of electrostatic attraction, positive and negative charges, you can use a functional group that you can change the charge by using a different solution pH. Or if you want to take advantage of short range van der Waals attractions, then you can use a self-assembled monolayer with a neutral head group, such as a methyl group. But in any event, using self-assembled monolayers on preformed nanostructures like gold nanowires or gold nanoparticles, that gives those nanomaterials functionality that you can change based on the nature of the head group. But in any event, we're going to use self-assembled monolayers in this case to create patterns or to etch patterns using the AFM tip. Now, as you can see in this STM image that was pulled from a 2017 article found in Langmuir, we have a very well-organized structure. Okay, we have this repeating structure in all directions. Okay, and the reason why we have such obvious periodicity is because the long carbon chains that we find in the alkane thiol molecules, they have these short-range intermolecular forces that locks the molecules in place. So we have this really tight molecular film, and that works to our advantage because the tight, well-organized arrangement that we see in self-assembled monolayers will provide us with an opportunity to produce really high-resolution patterns that we can etch using our scanning atomic force microscope tip. Now, next, what I'd like to do is I'd like to play a very short video for you that will provide you with an overview or a visual regarding some of the lithographic techniques we're going to discuss over the next several minutes. So once again, if you have any problems hearing the video or seeing it, just let me know.
Nanolithography. Here, the cantilever is used to intentionally modify the sample surface via mechanical and/or electrical means. To mechanically alter a surface, a specialized robust cantilever gouges the surface with excessive force. To electrically alter a surface, a cantilever with a high bias is used to oxidize local surface regions.
Okay, so that short video provided you with an overview of two of the nanofabrication techniques we're going to talk about. So the first technique that was illustrated in the video was nanoshaving. Okay, and the second is anodization lithography, which we'll get to in a few minutes. But nanoshaving, as the name implies, it involves the use of the AFM tip as a shaver, right? It simply goes through and rakes away or etches away regions in your molecular film. And that's what Glen will be demonstrating here shortly. So he set up the portable AFM unit, and he has a substrate that's been modified with the polymer film, and he'll be using the AFM tip to etch the film and then subsequently image the structures using one of the specialized techniques we'll talk about towards the end of this presentation. But in any event, as you can see in this picture, we start with a well-ordered molecular film or a self-assembled monolayer assembled on a gold substrate, okay? So if we want to initially image the self-assembled monolayers, we use a moderate to low set point because during imaging, all you want to do is trace your surface topography. Now, if you want to shave a particular region in your molecular film, you apply a higher than normal set point. And set point is the interactive force that you want maintained between your tip and the sample. So generally, we use anywhere between 10 to 15 nanonewtons in order to image in the labs our students the AFM labs or students conducting on campus. But in any event, we use much higher set points in order to etch away a region in our molecular film. Okay, and then Glenn, if you don't mind, when you get to your demonstration, if you can tell them the set points you use to image, and then the ones you use for etching for comparison's sake. So another version of nanoshaving is nanografting. Nanografting involves shaving away a particular region in your molecular film, and then you backfill the shaved region with a different alkane thiol molecule. Now, why would you want to do that? Okay. Now, let's say you want to create a multi-array sensor. Okay. Let's say you want to use a small glass substrate coated in gold. Okay. And then you assemble a self-assembled monolayer on your gold film. And on that 1 square inch wafer, let's say you want 5 different regions, each with a different sensing specificity. Okay. So you would start with a methyl terminated self-assembled monolayer, because generally methyl terminated self-assembled monolayers are neutral, right? The only interactions you would observe with methyl terminated self-assembled monolayers are the van der Waals interactions that involve very short range distances. But in any event, let's say that you want specific regions in that monolayer to sense, let's say, glucose levels or urea levels to test for kidney function, right? And then you have 3 other spots that can test for a different biological molecule in a small volume of sample. So what you can do in this case is you can etch away a particular region in your methyl terminated self-assembled monolayer and backfill it with different alkane thiols, each with a different head group. And the different head groups will allow those particular squares or circles to sense a different molecule in the sample. So yeah, Robert, go ahead and ask your question.
I was wondering, how do you how do you make it go up and down? Do you have to move the whole thing, the force microscope? Does it have to be moved mechanically, or do you do it electrostatically, or what do you do?
So you mean the probe? How do you move?
Yeah.
Right, sure. Very good question. So the probe motion is controlled by using a scanner. And the scanner consists of piezoelectric materials that have very small increments in terms of movement. So piezoelectric materials are ceramic materials that bend and contract in response to electrical applied voltage, applied potential, right? So when you send the DC pulse in one configuration, you will have an expansion. And if you reverse the polarity and then apply your voltage pulse, then you'll have a contraction, right? So we use a scanner with piezoelectric actuators to move the tip across the sample surface.
So you don't use the laser at all to?
Right. So let me go at the laser. No, the laser is just used to track tip sample motion, or excuse me, tip cantilever motion, because the cantilever is about 200 micrometers or 200 microns long, and the tip that's mounted on the underside at the end of the cantilever, that actually makes physical contact with the sample surface, right? And so the chip is mounted inside of the scanner. And then we type in the scan size or the area that we want to scan across our sample. And then the AFM electronics sends these appropriate signals to the scanner so that the tip is moved across the appropriate region. Right.
And the laser doesn't interact with the, I've heard that you can have laser pressure, or, from photons hitting a surface, but that's
right, like
what you
right,
have
like,
there is too small for that.
Right. So like in the case of a radiometer, when you shine the light on the veins turn. So is that what you're talking about? Something similar to that?
Well, they're going to send a laser sail out
right
to space, and they're going to push it with lasers, but these lasers are much smaller than that. I mean, the power is much less.
Right, we're dealing with extremely small laser power in this case, because again, we're not using the laser to move the cantilever or manipulate the surface in any way. We're simply using the laser as a means to track the tip motion as it moves across our sample surface.
And the laser footprint is so small that it's only hitting the cantilever?
Exactly right. As a matter of fact, in most AFM systems, you have to do what's called a laser alignment. So you actually have micrometers on the top of the scanner that control the position of the laser. So you have a stage micrometer in the X direction and one that controls the Y direction. So you move those stage micrometers so you can position the laser beam on the cantilever. And there's typically a frosted screen, a frosted lucite screen, or some other mechanism that allows you to watch the reflected laser beam as you move the stage micrometer, right? So the laser, again, the laser doesn't impact the motion of the cantilever, doesn't influence the motion of the tip. The laser's job is simply to provide us a means by which we can track the motion of the tip as it traces the sample surface.
Okay.
So we're using an extremely low power laser, nothing really fancy or exotic. This is very, very simple design. As a matter of fact, some older texts refer to this method as the beam bounce method or the optical lever method, because again, all the laser is doing is it's tracking the tip motion as the tip traces across the sample surface. Right, and then the reflected laser beam strikes this photodetector, and based on the position of the based on the position of the laser beam on the photodetector, that's going to determine that data is going to be used to create our 2D or 3D topography image on our computer screen.
Okay, and you have the stage so well controlled that you can move it in nanometers?
Right, well, the scanner, you can have two different types of AFM configurations. You can have what's called tip scanning or sample scanning. So all three of our AFM systems are tip scanning systems, which means we mount the tip on the probe, we mount that directly to the scanner, and the scanner moves the tip while the stage is stationary. And that's actually the best configuration, because if you have a sample scanning system where you have the piezo materials underneath the specimen or sample, then you run the risk of damaging the piezo ceramics when you take your sample on and off the stage. And also, when you use a sample scanning stage, you limit the size of sample you can use for that particular model. But that goes back to what I was saying about, your question goes back to what I was saying about the piezoelectric materials. Piezoelectric materials have step sizes that are less than a nanometer, like 1/10 of a nanometer, right? So these piezoelectric scanners are able to move the tip in sub-nanometer or angstrom increments, right? So, so that's why the scan. Go ahead.
Thank you.
Yeah, no problem. And that's why scanners use piezoelectric actuators rather than electromagnetic. Because if you use an electromagnetic actuator to move the scanner or move the tip, then your step sizes will be too large, right?
Yeah.
If you use an electromechanical actuator that has a smaller step sizes like a micron, you can forget about imaging gold nanoparticles or nanotubes, right? Because that step size is too large. So that's why AFM manufacturers use piezo ceramic materials so that they can move the probe in smaller step sizes so you can achieve atomic and nanoscale resolution. So there are a couple of graphics that I skipped that I want to get back to. This is an AFM image that I recorded back in my days at the Naval Research Lab in DC. This is an AFM image, lateral force or friction image. We'll talk about friction imaging a little bit later, where I imaged a square in a self-assembled monolayer containing mercaptohexadecanoic acid molecules or alkane thiols. Now, what I was trying to do at the time is I was trying to localize an area where we could facilitate the sticking of bacterial cells. Because at that time, I was conducting research involving metal-reducing bacteria such as Shigella and and geobacter. And those bacteria, they grow in colonies. So we wanted to image one or two cells at a time. So I used nanoshaving to try to localize an area where one or two bacterial cells would stick, so we can again perform our measurements on the nanofilaments growing out of the cell bodies. But in any event, this is typically how nanoshaving works. So this is one of many examples of what you can produce when you use your tip to etch or machine or produce a pattern in a self-assembled monolayer film. So this is an image that was actually, or a sample that was actually made by a student, Peter Ainsworth, back in 2012. So he actually used a small square of a CD, a polycarbonate CD, and he was able to etch our college name using nanoshaving on the back of the CD. So you can produce patterns that have dimensions tens of nanometers in size. Now, if you use a self-assembled monolayer as your initial substrate, then you can have a drastic increase in your resolution, which means your line widths will be very sharp and much smaller. And that's due to the dense packing that we observe in a self-assembled monolayer. So that's why self-assembled monolayers are oftentimes the thin films of choice when AFM lithography or nanoshaving is performed, because again, the dense packing of the monolayers allows the tip to make very accurate and very small line width etching in the resulting film. So the next technique I'd like to go over with you is dip pen nanolithography. And this is an animation that I like to play for you to give you a visual as to what dip pen nanolithography involves. So with dip pen nanolithography, we're actually using the AFM tip as an ink pen. This is a very clever method of lithography that was invented by Chad Merkin. He's a very famous chemist, teaches at Northwestern University. This is a technique that was invented by him in 1999. And what this technique involves loading the AFM tip with your molecules of interest. And once again, alkane thiol molecules are oftentimes used as the ink, right? And I'll talk about why here in just a second. So you load your AFM tip with the ink of interest, and then you lower the AFM tip until it makes contact with the sample surface. So when that happens, when the tip makes contact with the sample surface, a liquid meniscus is formed. The liquid meniscus is a little bridge that allows the molecules loaded on the tip. It allows these molecules to diffuse to the surface, allowing the AFM user to produce, to write patterns, okay? Now, the nanoshaving technique that we just discussed a few minutes ago, that is a subtractive technique. In that particular case, the AFM tip is etching away a particular region in your film. Dip pen nanolithography is an additive technique. In this particular case, you're using the AFM tip to add molecules or to deposit molecules on the sample surface.
In the first way, are you actually scraping the molecules off?
Yeah, you sure are. Yeah, the tip, it's like a snow plow in the wintertime, right? You see the plow plowing the roads. It's the exact same thing. Right, so yeah, so that's a subtractive technique, and this is an additive technique because in dip pen nanolithography, we're adding the molecules to the sample surface. So once again, we can achieve very precise, very accurate nanoscale structures using this method due to the shape and the geometry of the tip. We can produce lines as thin as 15 nanometers, and maybe even smaller if you use a tip that's been etched using focused ion beam or field milling. Now, there are a number of parameters that affect how well your pattern comes out when you deposit using dip pen nanolithography. Okay, so there are 5 main factors that affect how well your pattern that affect the resolution of the resulting pattern. So your tip radius. Okay, and like I said a second ago, if you have a tip that's been etched using reactive ion etching or focused ion beam, then you have a much smaller tip apex that will allow you to print and draw much smaller lines with a much smaller line width, right? Lines that are a lot thinner. Substrate roughness. Now this impacts dip pen nanolithography because like I said a couple minutes ago, the ink that's oftentimes used in dip pen nanolithography is an ink made using alkane thiols and alcohol, right? Alkane thiols are a very versatile molecule because they really like to stick to gold via the sulfur atom, and they have the head group that can be tailored in order to meet the needs of your research project. So in order to deposit an alkane thiol ink using dip pen nanolithography, you need to use a flat, smooth substrate. Oftentimes, the substrate that's used in dip pen nanolithography involves a substrate where the experimenter or the researcher takes a sheet of mica or HOPG, an atomically flat surface, and they evaporate gold using a metal evaporator or sputter coating. They evaporate gold on the surface of the mica or the HOPG. So in that particular case, you have an atomically flat gold surface, relatively free of defects that will allow the alkane thiols to effectively stick to the gold surface. Contact time affects the resolution of your resulting image. The longer you leave the tip on the surface, the more molecules that will diffuse to the surface, and that will increase the resolution of your pattern. Humidity impacts the resolution of your DPN structure because humidity is going to affect the size of the liquid meniscus that forms between the tip and the substrate. And remember, the liquid meniscus is the source of molecular transport. Okay, the liquid meniscus is how the molecules diffuse from the tip to the sample surface. And lastly, grain size of the substrate affects the resulting pattern appearance also. Because like I said a minute ago, oftentimes DPN involves using a substrate where we've evaporated gold on mica or HOPG for an atomically flat surface. When you do so, you have very, very few grain boundaries, and grain boundaries are basically the boundary or the interface between two grains that have different orientations. And these alkane thiol molecules really don't like to assemble on grain boundaries. So the fewest grain boundaries you have, the better quality image you'll produce with DPN. So this, once again, I'm drawing from my Naval Research Lab days, and I'm showing you an image, a lateral force microscope image of an attempt I made at DPN back as a postdoc at the Naval Research Lab. So in this particular case, I coated the AFM tip with mercaptohexadecanoic acid. And that's a molecule that contains 16 carbons. There's a carboxylic acid head group or functional group. And then we have the sulfur atom that attaches to the gold surface. So when we perform DPN, we take the tip and we actually insert it in the solution that we want, that contains the molecules that we want to coat the tip. So, you know, when I created this image, or when I performed this test, that's all I did. I took a little beaker, made a solution of the alkane thiol using alcohol, and then I put the tip in the solution and let it sit for a few minutes. And afterwards, you dry the tip, you lightly dry the tip because you still want to have enough moisture to form the liquid meniscus, load the tip in the AFM scanner, and then bring the tip down to the sample surface, and then control the scanner so that you can draw the pattern that you want deposited on your substrate. So these are two little circles that are deposited using DPN. And once again, I was hoping that these patterns would result in, I was hoping that these patterns would act as sticky pads that will allow one or two of the bacterial cells that I was studying. It would allow those cells to stick to these sticky pads. So spoiler alert, it didn't work. But in any event, there is a wide variety of literature that shows successful nanostructures printed using DPN. Here are just a couple of the many examples that you can find in the literature. This example here comes from a 2002 Nanoletters paper. And in this particular case, the researchers were able to deposit, I believe this is bovine serum albumin. They were able to deposit an array of this BSA protein on a clean flat surface. And then a report coming out of the Journal of Chemical Education, Journal of American Chemical Society, a 2003 report shows lysosomes and immunoglobulin, proteins deposited on a gold surface. So again, DPN is a very versatile technique that allows you to produce a variety of patterns using a variety of different inks. Okay, alkane thiols are the most commonly used ink, but you can use proteins and cells also as your ink, right? And you can use that biological ink to deposit a particular pattern on your gold or silver surface. So the next one, let me back up and talk really quickly about one other flavor of DPN. This is thermal DPN, okay? So as the name implies, thermal DPN involves the use of heat in order to deposit a polymer on a substrate surface. So in this particular case, the AFM probe needs to be, you need to apply voltage to the AFM probe. Now, the reason you want to do that is because you want the probe to heat up, okay? Now, now when you heat up the probe, what you're doing is you're allowing the polymer that's coating the probe, you allow that polymer to melt, right? So when you match or exceed the melting temperature of the polymer coating the tip, then you're able to draw lines. You're able to draw lines with 10 nanometer or smaller line widths on the surface of your preferred substrate. I like to refer to this method as a nanoscale hot glue gun, right? Because all you're doing is you're coating you first coat your AFM probe with your polymer of interest. Then you apply the voltage, the low voltage to your probe to melt the polymer. And then you use an AFM lithography program or lithography software to write the desired pattern. So the next technique involving DPN is an electrochemical method. This is electrochemical DPN. Now, unlike the other DPN methods we discussed previously, this method will involve the use of an electrolyte or fluid. Okay, so if you want to perform electrochemical DPN using AFM, you need to have a fluid cell attached to your sample stage. And a fluid cell is basically a small polymer corral with an O-ring, has about maybe a 1-inch diameter, and you're able to put your substrate and your fluid of choice inside of the fluid cell. And when you lower the scanner into the fluid cell, you're only lowering the tip, right? The tip is the only thing that's immersed when you use the fluid cell. But in any event, with electrochemical DPN, you're applying a voltage to the tip while the tip is immersed in the solution. So the solution is going to contain metal cations that you ultimately want to reduce when the appropriate voltage is applied to the tip. Okay, so let's say, for instance, you want to make silver strips. You want to make 10 nanometer wide silver strips. So what you would do is you would put silver nitrate, a dilute concentration of silver nitrate, in your fluid cell, okay? Then you would lower the tip as you normally would during a normal AFM scan. But in this particular case, you would want a small separation between your tip and the sample, right? So when you apply the appropriate voltage, you would facilitate reduction of the silver ions directly under the tip. Okay, so once again, this is a form of electrochemical DPN that doesn't involve the use of an ink per se. It involves the use of reduction of metal cations directly under the tip in order to deposit your structure of interest. So the last type of lithography I want to discuss with you before we get into our specialized AFM imaging modes and then Glen's demonstration is anodization lithography, okay? Now, anodization lithography is somewhat similar to electrochemical DPN, okay? So there's some key differences between the two. In the case of electrochemical DPN, that involves the use of a fluid, and number two, you are reducing metal cations directly under the AFM tip. And then number three, the electrochemical DPN involves a gap or a space between the tip and the sample, okay? So again, with electrochemical DPN, you need to have metal cations in solution that you're ultimately going to reduce. In order to reduce those metal cations under the tip, you need a tip sample spacing. But in the case of anodization lithography, you're making direct contact with the sample. Okay, you're making direct contact with the sample surface, and you're performing this technique in air under ambient conditions, right? Well, previously with electrochemical DPN, you needed a fluid cell and an electrolyte, okay? So according to reports, we generally use between 2 and 20 volts in order to facilitate oxidation of the substrate directly under the AFM tip. And one of the things that I really like about this technique, again, full disclosure, I've never done it before, but when I was reading about this technique to prepare for this presentation, a really interesting fact to learn about this technique is that the resulting structures can act as negative or positive masks. Okay, now I'll tell you what I mean by that. Let me talk about a unrelated printing technique, which is photolithography. Okay, so I'm sure everybody in here have heard of photolithography and know basically how it works. You use light, you shine UV light through a mask, and then the mask pattern is reproduced in a photoresist. Okay, a photoresist that's coating a silicon wafer. So in the case of photolithography, you can have a positive resist or a negative resist. So if you have a positive resist, the areas that are exposed with UV light, those areas weaken, right? The chemical bonds in those areas are weakened, and those particular areas are rinsed away with a developer solution. Now, in the case of a negative resist, the exposed regions are hardened, right? Because the bonds are strengthened or the polymer cross-links, right? So in one case, with a positive resist, you're rinsing away the exposed areas to leave a trench in the photoresist. And in the case of the negative resist, you're rinsing away the unexposed areas. So the areas that are exposed to the UV light, they remain and they form a step. And the reason why I'm bringing that up is because anodization lithography achieves the exact same thing, okay? So here's an example of that, and that comes out of Applied Physics A, a 1998 article from that journal, where IBM researchers use anodization lithography in order to create a negative and a positive image, right? So with this technique, the resulting oxidized area can act as a mask, right? So let's say that there's some areas underneath the resist or underneath the areas underneath the oxidized pattern that you want to protect. Well, the oxidized pattern will protect the underlying layer, underlying substrate if you want to perform a subsequent etching step. So in this particular case, the oxidized pattern remains so that you can etch away all the exposed substrate. So this is the oxidized pattern acting as a protecting layer or acting as a negative resist. Now, in the opposite end, you can have a case where you perform anodization lithography, you have your oxidized pattern, and then in this particular case, you etch the pattern away. So now you have trenches or holes in your substrate. So in this case, the oxidized pattern acts as in a positive sense because the oxidized pattern is washed away, leaving behind trenches in the resulting substrate. So this is one really interesting fact that I learned about anodization lithography, the fact that you can use the resulting oxidized surface and as a negative protecting layer or as a positive layer in which you want to subsequently etch the oxidized region away. So before I get into the specialized operating modes of AFM that are used to image these structures that are made using AFM lithography, I want to pause for a second to see if anybody has any questions. You can ask your question in the chat, or you can just unmute yourself and I'll try to help you as best I can.
I have a question.
Sure.
Is there any kind of operation like this where you don't use the atomic force microscope and you just use the laser to, like in the liquid, where you can, when you get a much finer or higher resolution with just using a laser light to make your image rather than using the atomic force microscope?
Right. So I do know that there's this technique known as laser-induced desorption, where you use the laser beam directly to break chemical bonds between an absorbate and a substrate. So your absorbate is like an alkane thiol molecule, like I discussed before, and then you have like a substrate. So your molecule is attached to your substrate via chemical bond. So with laser-induced desorption, the laser comes in and breaks that bond. So you can basically do the same thing. You can like etch patterns in your substrate or in your film, your thin film, using the laser. Now, full disclosure, that's all I know about that technique. I don't know anything about the feature size that you can achieve using laser-induced desorption, but I do know that you can. It's used to perform basically the exact same thing.
Yeah, maybe I can also add up to what Wes was saying.
Sure.
Great presentation, by the way, Wes. So far, I was closely looking at your slides. So the lasers, generally, when we talk about the lasers, we should always think about their wavelengths too. So that's still like under the main frame of optical sense of patterning. So the wavelength is still like 200 nanometers up to some couple of 100 nanometers too, but it's still quite large for patterning purposes. So most of the time when you do patterning with lasers, like laser direct writing, etc., too, for say photomask writing, they're generally limited by the wavelengths. And we have also the 3D printing with lasers, like you can create all these sculpturing with lasers as well. But again, like Wes was saying, they're going to be really much larger than what AFM would probably, or SPM in general, would offer to you. But yeah, there might be some exceptional cases that I might not be familiar with, but I would say most likely they are not going to be coming outcome of a direct writing or direct interaction with the laser beam, because it's going to be very tough to focus that into a certain region with a precision that's smaller than an AFM tip can do. Thank you.
No, thank you, Austin. Thank you. All right, anybody else? No? Okay. All right. So I'm going to take about 30-ish minutes to talk about the specialized AFM operating modes, because I want to leave ample time for Glen's demo. We might end a little earlier than that. I might do 25 or so, again, to give Glen's ample time to show you the technique and image the resulting structure. But in any event, AFM generally has three main operating modes: contact mode where the tip is making direct contact with the sample surface. We have non-contact mode where we have an oscillating tip that's held about 1 nanometer away from the sample surface. And then we have tapping mode where the tip actually taps the sample surface. Now I'm going to focus on lateral force microscopy, LFM, and phase imaging. Now, the reason I want to focus on those two imaging techniques in particular is because they are oftentimes used to image the nanoscale structures that are made using the fabrication techniques that I mentioned previously. So I'm going to start with lateral force microscopy, that's also known as frictional force microscopy. So what I'd like to do is I'd like to play a short, very short animation that will provide you with a visual as to how LFM works.
LFM. While more traditional AFM techniques focus on vertical deflections of the cantilever to image the surface topography, lateral force microscopy, LFM, instead focuses on torsional deflections of the cantilever scan across the surface. The amount the cantilever twists as the tip is dragged across the sample surface provides useful insight into the frictional force and adhesion properties of the sample.
Okay, and I want to stop it right there so we can focus on these two plots. Now, these plots are known as trace-retrace plots. And what that means is as an AFM user, as your tip or probe is scanning your sample surface, the AFM will record in real time line by line traces as the tip is scanning your surface. Yeah, Robert, go ahead. It said Robert says you have a, tell me in the chat you have another question.
No, I'll take my hand down. Sorry, I thought it.
No problem. So with lateral force microscopy, we need to have the system, the AFM system, operating in contact mode. So that means the tip is making direct contact with the sample surface. Now, when we image in contact mode, what we're doing is we're relying solely on the cantilever's vertical deflection in order to record our surface topography. Okay, so that's one of the key advantages of contact mode. By making direct contact with the sample surface, the tip is extremely sensitive to any variations in height across our substrate. Now, what happens if we have a thin molecular film like a self-assembled monolayer or a spin-coated polymer on a wafer where we don't see very many variations in sample height, right? Then what do? So in that particular case, you can use lateral force microscopy. Because as you can see in this first trace-retrace plot, in our topography plot, you see there's basically a flat line. What that means is for that particular line scan, remember the trace-retrace plot is simply a real-time view of the current line scan that the probe is making, okay? So in this particular case, the probe is not detecting any discernible height variation. But let's look at this bottom curve. This is known as our friction loop. And I'll talk more about it here in just a second. In this particular friction loop, we see a step when we go in the positive X direction, and then we see a negative step when we go in the negative X direction. Now, what causes us to have a trace-retrace plot that gives us two different loops? Well, in this particular case, the tip is experiencing variations in frictional forces as it scans across the sample surface. So one of the major advantages of lateral force microscopy is that it takes advantage of differences in friction across our sample surface in order for us to characterize material differences, right? So let's say, for the sake of argument, you have a block copolymer containing polymethyl methacrylate and polystyrene. So if you were to spin coat that copolymer on a wafer and image it using contact mode AFM, you're not going to see much in terms of surface topography because, again, you'll have a nice flat layer of your copolymer. However, if you use lateral force microscopy to image your copolymer spun on your wafer, you will see that the cantilever actually twists as it goes across the sample surface. And the degree that the cantilever twists, I'll use this image, the degree that the cantilever twists depends upon the coefficients of friction of the components in your material. So if you have a really rough material or a rough constituent in your film, then the cantilever is going to twist to a great extent. And if you have a smoother component or constituent in your film, then the cantilever is not going to twist as much, right? So again, the AFM tip is very sensitive to differences in frictional forces. And the frictional forces arise from the atoms or molecules between the tip and the sample making contact, right? Because if we look at something with an unaided eye, without the use of a microscope, or even if we use a 100x objective on an optical microscope, a sample may still look relatively smooth. But if we look at the sample, if we look at the tip and our sample of interest on an atomic level, we'll see that the atoms or molecules actually resembles a mountain range, right? And so the contact between these two mountain ranges, right, between the tip and the sample, that's what leads to friction. And we're able to quantify and image and measure the interaction between the mountain ranges by using lateral force microscopy. Now, there are two forces that we have to consider when we use lateral force microscopy. There's the normal force that's set by the set point, that's the user-defined set point. And then there's the frictional force, okay? And the frictional forces comes from the interaction between tip atoms and sample atoms. And so as the tip operates under the, as the AFM system operates in the lateral force microscope mode, we have our standard vertical deflection that allows us to continue to record surface topography. And we also have a lateral motion, right? The laser spot can move horizontally across the photodetector due to the twisting motion of the cantilever. So what that means is this. That means we can record topography and friction at the same time using lateral force microscopy. So how does the computer signal tell how does the computer or the AFM electronics, how does it tell the difference between the topography signal and the lateral force or friction signal? So we're able to do that because the photodetector is divided up into 4 quadrants, okay, labeled A, B, C, and D, okay? So in order to record surface topography, the AFM electronics compares the top quadrants, A and B, to the bottom quadrants, C and D. So that's how the AFM system records topography. So at the same time, the AFM electronics monitor and compare quadrants A and C to quadrants B and D. So that comparison allows the system to record frictional data. So that's how you're able to record surface topography and friction simultaneously while conducting an LFM scan. So this is a really nice image that I pulled from a article that comes out of Surface Science, a 2008 article from Surface Science. So the researchers in this case have HOPG, highly oriented pyrolytic graphite, as the substrate, and then they've deposited some flakes of oxidized graphene. So graphene is basically a hexagonal arrangement of carbon atoms that's 1 carbon atom thick. So that would be very hard to discern using standard topographical image, right? So if you were simply to record the surface topography of this particular sample, you wouldn't see much, right? Because the height or the thickness of the oxidized graphene is simply 1 carbon atom, right? And then you have this phenomenon called tip sample convolution that'll make it very difficult to see something so flat. But in any event, we can clearly see the oxidized graphene flakes in this image, right? That's because the oxidized graphene flakes have higher frictional forces. We observe higher frictional forces between the oxidized graphene and the AFM tip, okay? Now the question is, how do I know that the bright region is the oxidized graphene? Well, they label it in the image, but if they didn't label it, how would I know? Well, the Areas that exhibit higher coefficients of friction or rougher areas, they appear brighter in lateral force microscope images, right? The rougher areas or rougher surfaces appear brighter in a lateral force microscope image. Now, why is that? Let me go back. Let me go back to this. Let me go back to this image here. So if we have a really rough surface, that means the reflected laser beam is going to move a larger horizontal distance across the photodetector. When the laser beam moves a larger horizontal distance across the photodetector, it's going to generate a higher analog voltage that's then processed to create the LFM image. If we have a smoother surface, if the tip traces over smoother surface, then we're going to have less twisting observed with the cantilever. So that means the reflected laser beam is going to move a smaller distance, a smaller horizontal distance across the photodetector, generating a smaller analog voltage that's then processed to create our LFM image. So that's how the AFM system is able to discern rough areas from smooth areas, by how far the reflected laser beam moves horizontally across the photodetector. So here's a image I really like. This is some research that was published in 2015 in a copy of Sensors. I really like what the researchers did here, because as a chemist, I can really appreciate what's being shown. So these researchers patterned an octadecane thiol and a mercapto undecanoic acid monolayer on the surface of gold. Okay, so these alkane thiol thin films are ridiculously thin, extremely thin. So it would be very hard to observe the topography using standard contact mode. But with lateral force microscopy, you can clearly see the 3 different regions in the LFM image. Okay, this darker area, that's our octadecane thiol region. This mid-range color, this is our gold region. And then the brighter area is the mercapto undecanoic acid region. So the undecanoic acid region appears brighter than the gold and the ODT region. And the reason for that is because the AFM tip that was used in this particular case is coated with a self-assembled monolayer with an amine functional group, which is a base, right? And undecanoic acid contains carboxylic acid self-assembled monolayers. So as the AFM tip has a base at the around its periphery, as the AFM tip scans the sample surface, we can clearly see we have acid-base interactions occurring between the tip and the undecanoic acid, right? So those stronger chemical interactions is going to generate higher friction that we can clearly see in the LFM image because those regions appear brighter. So the reason I wanted to incorporate this particular slide in this presentation is to show you that you can use LFM not only to image patterns fabricated using the AFM tip, but you can also sense differences in chemical specificities along your sample surface using this technique also. Because if you have a greater interaction between your tip and the sample, that's going to generate higher friction, which will allow your that particular region to appear brighter. So this is I believe I showed you this image before. This is an LFM image of alkane thiol dots printed on a gold surface using dip pen nanolithography. So really quickly, I want to talk to you about the frictional loop because I need to talk about one other AFM technique before we get to Glen's demo. So the friction loop, I showed you this earlier. We have in one direction, we have one particular response. And then when we scan in the opposite direction, we have a different response. Now, why is that? Now, as the tip is skating across the sample surface during an LFM scan, you'll notice that the forward direction and the reverse direction will never be the same. And the reason for that is because as the tip traces, goes in the forward direction and then subsequently goes in the reverse direction, it's going to experience different frictional forces, okay? So the forward and reverse retrace plots in an LFM scan will be opposite of each other, right? Because when the tip goes in the reverse direction, it's sensing the frictional forces in the opposite order, right? So that's why you have a different signal in your friction loop when you compare the forward scan to the reverse scan. Now, the friction loop, it might not appear to be much, but you can obtain some very valuable information from the friction loop. And that valuable information has to do with the coefficients of friction of the components in your material, in your sample. So if you have a larger difference, if you have a larger signal difference between your forward scan and reverse scans, that means you're traveling over the tip is traveling over a really rough area. So that particular region has a high coefficient of friction. Now, if you have a smaller signal difference between your forward and reverse scan, that means you're traveling over a smoother area, right? So you have you're over a region with a lower coefficient of friction, denoted by the symbol mu, okay? So that's a way you can kind of qualitatively estimate or assess your coefficients of friction in a multi-component sample by using the friction loop. Now, you can also quantitatively determine your coefficient of friction. And really quickly, I'll go through how you obtain that. So, like I said before, during LFM scanning, the tip experiences two forces: the normal force that's applied by the user via the set point, and the frictional forces that the tip experiences as it scans the sample. So by using this very simple equation, you can see the relationship between the frictional forces, the normal forces, and the coefficient of friction. So what you can do is simply graph the frictional forces on the y-axis and the normal forces on the x-axis, plot your data points, and the slope of this line will give you your coefficient of friction. So it seems simple enough, but the fact that we're using frictional forces and normal forces to determine our mu value, that complicates things. So normally, during standard AFM topography imaging, we simply concern ourselves with one spring constant, the vertical spring constant, because that's going to tell us how much our cantilever is going to bend as the tip traces the sample surface. But in lateral force microscopy, since frictional forces are a big deal, we have to take into consideration the torsional spring constant, the KT value, okay? So the KT value is important is because we're relying on the twisting motion of the cantilever in order to record our frictional forces. So as you can see, just like in the case of our vertical spring constant, the torsional spring constant also takes into consideration the physical dimensions of the probe that you're using. And the physical dimension data is not hard to find. You can easily find the physical dimension data on the probe manufacturer's website. So once you've determined your torsional spring constant, to determine your frictional forces between the tip and the sample, you can determine your photodetector sensitivity and the friction loop signal. And these three data points will give you your frictional force value. So really quickly, to find your torsional photodetector sensitivity, you just consider how much the photodetector signal, the friction signal, goes up every micron the tip is moved. So that's how you determine your photodetector sensitivity. And then your delta V value, your difference in signal, that's simply the difference between the friction loop plot and the baseline. And so once you determine all those values, you have your frictional force data that you plot on the y-axis. You plot your normal force data on the x-axis. And when you plot that resulting data points, you can find your coefficient of friction. So before I talk about the last imaging technique that we use to see the nanostructures printed using AFM, Does anybody have any questions regarding LFM, also known as frictional force microscopy?
I'm still not, if you take a point and you scrape it along one direction, are you actually changing the orientation of the molecules on the surface? And so that when you go back over it, you're going back over the same position, then you're getting that a difference in friction force?
Right. So yeah, let me go back. This would be a better graphic to use to answer your question. So and this is something I should have emphasized a few minutes ago. When you use lateral force microscopy, you're operating under normal contact mode conditions, which means you're using a really low set point. So as an AFM user, you would enter in a set point that allows a tip to make contact with the sample just enough just to trace the surface topography. Right, so the tip sample interactions is on the order of nanonewtons. So it's an extremely gentle interaction between the tip and the sample. Now we can change that by jacking up the set point. Like if we want to do nanoshaving, we use a 20+ nanonewton set point and we can shave away all day. But in the case of LFM or frictional force microscopy, we want a gentle tip sample interaction. We want the interaction to be just enough so that the tip can just lightly trace the sample surface. So while we're recording our frictional data, we're not changing the surface at all, right? Now that changes if we use a higher set point, right? So for instance, let me go to this image. This is a square that was etched in a polymer film. This is like some student data that was recorded 4 or 5 years ago. And this will be very similar to what Glen is going to show you here in just a couple minutes. But in any event, this is the friction loop for one line scan, okay? So in the friction loop, you can see that the polymer regions, they produce a lower photodetector signal response. And the glass region, the wider square, the rougher area, that produces a higher photodetector response, right? So as we're scanning the surface in LFM, we're not changing the sample surface. We're just relying on the twisting motion of the cantilever to tell us what area is rougher and which area is higher.
So you're saying that as you're doing this, in one direction you get one friction constant, and in the opposite direction, over the same line, you get a different friction surface. Is that correct?
Well, right. Okay, so the surface doesn't change, right? What's changing is the tip scan direction and tip tilt.
Oh, I see. Tilts in the torsion is in an opposite direction.
Exactly.
I see.
Like in this image here, like you can see, you go by the colors on the grayscale colors, it's the same sample. The grayscale colors don't change, right?
Okay. Yeah.
But the order in which the tip traces over, the order of the components that the tip traces over changes, right?
Thank you.
Yeah, okay. All right, I guess I answered your question. Okay. All right, any other questions about LFM or frictional force microscopy? No? All right, so the last technique we'll talk about before Glen gets his demo is phase imaging. So I'm gonna skip over a lot of this just so we can get to Glen's demo and give y'all an opportunity for remote access to control the microscope remotely if that's something you wanna do. But phase imaging is a version of tapping mode AFM, okay? Tapping mode AFM involves oscillating the tip in a 100 nanometer range, right? So between the tip and the free space oscillation, there's a 100 nanometer range or space, okay? So the tip is oscillating in that space, and it's at one point is away from the sample surface, at the other point is tapping the sample surface. So in order to promote tapping mode, or in order to use tapping mode AFM, we need to determine the resonant frequency of our cantilever. because the resonant frequency of our cantilever is going to be where we have the maximum vibrational amplitude. And vibrational amplitude is the way we record surface topography using tapping mode, okay? So generally, when you use tapping mode AFM, one of the first things you do is you tune your cantilever. So that simply means this AFM system automatically determines the set point of the resonant frequency, right? You just hit a couple buttons and the system determines the resonant frequency for you, okay? So this is just a representation of the some tuning data where you have your photodetector signal response versus the cantilever frequency. And as you can see, the resonant frequency gives us the highest photodetector response. Now, in conjunction with determining your resonant frequency, when you conduct tuning with the AFM, the tuning data also includes what's called a Bode plot. And a Bode plot is a plot that has your what's called your phase angle on the y-axis and your frequency on the x-axis. So while the AFM system is determining your resonant frequency, it's monitoring a difference between your measured frequency and your drive frequency. The drive frequency is the frequency that's fed to the cantilever so that it will oscillate. Okay, the measured frequency is the frequency that's measured by the photodetector, because as the tapping tip makes contact with the sample surface, the frequency of oscillation is going to change based on the nature of the sample surface. Okay, so if you notice in the sample data, at the resonant frequency, we have a phase shift of approximately 90 degrees. Now, why is that? Now, as part of the AFM electronics for tapping mode, there's this device known as a lock-in amplifier. And I had planned to talk a little bit about the lock-in amplifier, but I'm running a little long time. But basically, the lock-in amplifier just takes the drive frequency, creates a duplicate, a 90-degree phase shift duplicate of the drive frequency, so that you can have two signals coming from your tapping mode data. Your amplitude data that provides your topography, and your phase data, which provides you information regarding the material properties of your sample. Now, why is phase data a big deal? Well, phase data is a big deal because it's the oscillating tip is very sensitive to changes in the softness of your sample. Right, so if you're over a relatively smooth area, you're not going to see much in terms of a difference between your drive frequency and your measured frequency. Your drive frequency in this case is your gray waveform. Measured frequency is your blue waveform. So if we're over a consistent area, a consistently fairly robust, smooth area, there's not going to be much of a difference between your drive and your measured frequency. Now, if we're over a softer, a more viscous area, then your measured frequency is going to be dampened, right? The oscillation is going to be dampened as the tip is tracing over the softer area. So you're going to have a substantial phase shift between your drive frequency and your measured frequency, right? So it's that phase shift that allows us to assess the material properties throughout our sample surface. Let me give you one example of that. This is a lab that Glen and I worked on. We're trying to design this for our AFM course, where we had the students print polymer structures using micro contact printing. Okay, so they're very, very thin polymer structures. So in the topography image, you can barely make out the polymer pattern. Okay. But in the phase image, you can clearly see the polymer pattern because it's a completely different color than the glass, okay? Now, in the case of phase imaging, what happens is this: softer areas appear darker in your phase image, right? Because we have significant damping of the resonant frequency of our vibrating tip. And then when the vibrating tip traces over a more robust or stiffer or harder area, the frequency is shifted to higher values. And so those areas are going to appear brighter in our phase image, okay? So in any event, why did I bother bringing up phase imaging? Well, you can see from the previous image that phase imaging is very sensitive to the detection of polymer structures on hard, flat surfaces, right? So if we use DPN or if we use electrochemical DPN to deposit an electroactive polymer or a non-conductive polymer on the surface, we may not be able to see the resulting structure using normal topography, right? But presumably the polymer will have a lower elasticity. So what that means is it's going to significantly dampen the frequency of the oscillating cantilever, which will allow us to pick it up in our phase image, okay? So here's some other applications involving phase imaging. We can use it to identify contaminants on the sample surface. We can map. We can create a compositional map of a sample containing more than one constituent, and that's what we've done here. You can discern between regions of high and low surface adhesion or high and low hardness. And you can also map electrical and magnetic properties using this technique. And that has implications when you're trying to design hard disks for data storage devices and other semiconductor products. So with that, I'd like to thank you for your attendance. I really appreciate you taking time to hear my presentation. So if you have any other questions regarding lecture content or any other general AFM questions, feel free to email me. And Glen is about to start a AFM demo here in a second. But if you want to reach out to Glen to schedule a remote AFM session, here's his contact email. And I want to point out that we are both conducting office hours next week. My office hours will be, let's see, 5:30 to 6:30 Eastern time next Tuesday the 13th. And I believe Glen said this is going to be Wednesday of next week at the same time. So Glen, is that right?
Yeah, that's correct. Same time.
Okay. All right. Okay, well, good. So I stopped a little early so we can have Glen take over and show us the nanoshaving and phase demo. So Glen, you're up. And again, everybody, thank you for your attendance.
Thank you.
Yeah, so before I get started, I see that Lily put a question down of, can you use AFM to provide an image of a tissue cell? Yes, you can. I believe it's done in the fluid cells. Wes, if you want to add anything to that, you can, but I know that you can look at tissue cells with AFM.
That's right. You want to use a fluid cell and you want to use tapping mode. So you can, you want to use non-contact mode so the tip doesn't damage the cell membrane.
Thank you. So before I get, oh, someone else have something?
I have one other question. Have you ever used, or do you guys ever use superconductors in any of this? Superconducting materials instead of gold, or can you have a superconductor as your base?
So in terms of superconducting materials, you'll be interested in studying the magnetic properties. Is that right?
Just in the process that you're using, are superconductors ever used in any phase?
What we do, well, on our campus, short answer, no. But if I'll tell you this, if you are, it may not directly answer your question, but if you're solely interested in studying the magnetic properties of materials, then there's a flavor of AFM that allows you to do that. It's called magnetic force microscopy. And so that has a specialized tip that can image nanoscale domains. And I know that hard disk manufacturers like Seagate, they use MFM in order to characterize their hard disk. So in the case of superconductors, if you're interested in studying the magnetic properties of those materials, then yes, there's a flavor of MFM, flavor of AFM that will allow you to do that. But that's something that we don't do. So, and there may be some other applications superconducting applications applied to AFM. I just don't know any off the top of my head.
Thanks.
Okay, so before I get started, I'm going to show you guys a short video. This was done last semester because of COVID, and we weren't able to meet in the lab. I went in and recorded all the labs for the students to watch, and then we performed them all remotely later on. So I kind of condensed this, and hopefully it'll give you guys a very brief general example of how some of this operation works with nanolithography. We'll start back here at the beginning and try again.
Our sample, the substrate is about a 2 square centimeter piece of microscope slide or glass. And we're going to apply PVP, which is a polymer solution. We're going to apply some of that to the surface of the glass and spin coat it. We're going to do 2 depositions. And what that should leave us with is a thin film of PVP, so we can then go and use the tip to etch some of that away. So for our mode, we're going to run this in contact mode because we're going to keep that tip in constant contact with our sample. Set point is crucial. It's currently set in volts. We don't want it set in volts. Remember, we're applying a pressure. So we want to set this to nanonewtons. And if you recall, whenever we image, we usually have our set point between 10 and 20, but we're not ready to image just yet. Right now, we want to etch away some of this PVP. So I'm going to increase the set point to 40, and that should be sufficient to remove the PVP in the area that is being scanned. And then later, we can reduce that to image what we have left behind. And now we'll come down, and this is our field of view, the scan area. So notice this green grid. This yellow box is our scan area. We're currently set at 40 microns. So I'm going to start off at just 10 microns. I want to etch a small area. So I'm going to go ahead and start the scan. And I'll move over to the screen with our scan images. Okay, so now you can see our areas where we're going to see our scan imaging. So this will see our topography, and over here it's set at friction. So this will show our lateral force or friction of the PVP and the glass. So I can see the topography of my glass. Glass is not perfectly smooth. And I can also see the friction data of that also. This will scan continuously until we stop it. So what I'm going to do is let this scan all the way up and then turn around and come back down. I want to do two passes on this area. That way I remove as much PVP in this area that I possibly can. Okay, so as this finishes its second scan, if you notice now, arrow's pointing down. To go all the way up and back down, even on its the fastest lines per second, it's been about 15 minutes. When this finishes, we're simply going to stop the scan and we're going to zoom out, and we do so by changing the field of view. Instead of 10 microns, we change it to something larger. At this point, we can go ahead and stop our scan. Now all we need to do is make a couple of adjustments. We need to change our set point. We don't want to keep it at 40 because then anything that the tip touches is going to scrape away. We want to go back to something that's good for imaging. So I'm going to put this at 10. Now we're going to keep everything the same except for our field of view, our scan area. So instead of 10 microns, we're going to change this to 40. Then all we have to do is restart the scan. So it's going to start at the bottom and work its way up to the top. Right now, we are still only scanning PVP. As we make our way up, what we're going to look for is the area that was etched away. So now we're starting to see the area that we etched. On the topography, you can see this. This is just the glass. And our PVP is surrounding this area of the glass. On our friction, you can definitely tell the glass because it's much, much darker than the surrounding PVP. But you can, again, you can definitely see your differences in topography, and you can definitely see your differences in friction or lateral force.
Okay, so this was an example of frictional force microscopy or lateral force. So in the other demonstration, I'm going to show you phase, or attempt to show you phase if the microscope will behave. Okay, we're all set. Okay, so I'll move on to show you what our other microscope looks like. The one I just showed you is in our lab and it's not online. So we're not able to use that one remotely, which is why I made videos and shared those. The one that I have now, it's similar to another one in our lab, but it's portable. So I'm in my basement right now and we will see if it will behave for us. But this is what it's going to look like when we open it up. So the sample that I have in here, it's the exact same as what I used on that other microscope. So it's a microscope slide substrate that has a thin coating of PVP that's been spin coated on that. Previously, I had a contact probe in, and you can see over here in the video, this little cantilever sticking out. A contact probe is a lot longer, so it would come out here somewhere. But then I went through the same process. I raised my set point. You can see over here, it's currently set at 20. I haven't changed anything yet. I would have turned this up to say 40 again, scanned an area of maybe 10 microns, and then I would be able to image that area. But in order to do phase, I need an oscillating tip or a tapping tip. So I had to take out the contact tip and put in an oscillating tip. Now the challenge is to find that same spot that I had just etched, which is only 10 microns. That is one of the areas that I'm having trouble with this morning, is I haven't been able to find it yet. But I have found, looks like some couple little bubbles that happen on this. And I think if we scan over these areas, it might give us a good representation of what that phase would look like if it were, you know, a square area that we had scanned. So I think that's what I'm going to try to do. And we'll just see how this works out. If you have any questions along the way, feel free to put them in chat or just speak up and I'll do my best to answer those. So I haven't done anything as far as parameters. So the first thing that I want to do is I want to make sure that I'm in the proper mode. Currently I'm in the static mode, which is also contact. I want to put this in phase. When I do so, it's going to open up another imaging panel. And just so you know, this far left one, this is going to be our topography, where we have our amplitude. This is going to be the raw data from the photodetector. And then we're going to have a third image of phase. Also, I need to make sure that I have the proper probe selected. So for this phase, we want to make sure that we have a tapping probe selected. And then I can go through and start setting up my parameters. I'll set up or start with a large field of view. For this, we want to see as much as we can. And I'm going to do a relatively quick scan speed. And the reason we start off with the quick scan speed is if we're in an area that we don't see anything of interest, there's no reason in wasting time staying here. I'd rather waste 1 minute than waste 10 minutes. So if we're not seeing anything that's of interest, we withdraw the tip and we can move somewhere else and try a different area. Points per line, I like to run mine at 512. And this is how many, we go positive X, negative X, and then up 1Y. How many lines of data are we going to obtain in this image? While I'm here, I do want to point out your scan speed and your points per line is going to dictate your acquisition time. So if I take this points per line, for example, and I go from 512 and I jump it up to 1024, I'm going to double the amount of time it's going to take to acquire this image. Am I going to gain much more resolution? Maybe not as enough to make it worthy of changing that to double my acquisition time. See, I meant to make that at 0.2. There we go. Rotation, I don't worry about. It's just rotating the direction of the scan. But our set point, if you recall, when we were doing an etch or when we're in contact mode, our set point, the units is nanonewtons, because we want to maintain a constant force between that tip sample interaction. When we are in tapping mode, we set this as a percentage. So if you can imagine a tip oscillating in air, that is going to be 100%. So how much do we want to dampen that will tell us how hard we're actually tapping the surface. 50% typically works well for some of these samples. So that's what I'll just keep it at for now. And then our gains are used to optimize the image once we find an area of interest, and we can use that to try to resolve better features. So I just quickly go through here, set up my initial parameters, and then I need to approach my sample, or I'm sorry, my tip to the sample surface. I've already brought it down fairly close. I wanted to save a little bit of time, so I brought it down to where it's very close to that sample surface. I can manually move it with this advance, and then also have a retract. And these are, longer I hold down on it, the more it moves. If I keep holding down onto it, I smash the cantilever into the surface and we start all over. So I won't do that. I also have a fine approach, and I like to say that as awesome as I am, I can't tell what 50% of that vibrational amplitude is, but the microscope can. So I'm going to select that and let it dictate it. When I do select that, you notice that it's running this frequency sweep. It automatically does it every time I do a fine approach. So after it does that frequency sweep, right now, if you look at this lower left, it says that I'm moving. My cantilever is very slowly moving down close to that sample surface. It's oscillating at 100%. And then once it makes contact with the sample surface and that vibrational amplitude has been dampened by 50%, because that's what I have my set point at, then it's going to prompt me like it did right there. My approach is done, and now I can begin scanning. So I'll hit OK, and we'll see how well this works. This is where I've had some issues with the microscope this morning. So let's see how this turns out. So as this scans, well, it's looking really rough. We'll see if we can make this look better. As this collects its data, I want to point out that on our topography, whatever is brighter is higher. So even if I'm not on an area where I etched out that pattern earlier, there's still debris on this. Like I said, I'm in my basement. I'm not in the lab setting. It's not the cleanest sample because I don't have a sonicator, so there's debris on it. And you'll see some of these bright specks. Those are taller features. So that's when we look at topography, that's how we can point out taller features as bright and dark. You can kind of see it on this deflection scan, but I wanted you to point out on the phase, you're going to notice that there's going to be some areas where it looks a little bit, in this case, darker. So that's going to show us where this is basically a film of PVP. So where you have these darker areas, that is going to have a different stiffness than the surrounding PVP because we're getting a different contrast. So remember what the phase is actually doing. It's tapping the surface and it's asking, is this hard or is this soft? And it's going to show us with contrast. So if you look at your topography, we see a nice bright area right here. So it's tall. We can also see it on our deflection scan, our amplitude, but we'll ignore that for now. But on our phase, we can tell that it has a different stiffness than the surrounding PVP. So if everything would have worked out for me today, which in typical fashion it didn't, I would have had a nice square area where I had etched away PVP, just like you saw in that video. In that video, I was able to just use the same probe, though. It was always a contact probe because I wasn't doing phase, I was doing frictional force. I didn't meet the challenge of that, so we're not seeing that etched out area. But I hope you're able to tell that what the topography looks like and what the phase would look like. While this finishes scanning a little bit, and it looks like we might be coming to a little feature up here. Luckily, I had saved a screenshot previously of what this is supposed to look like. And if I can get this zoom up here, I will show you. Okay, So this is a screen capture. And again, it shows a topography, and it's really hard to see any changes in topography because remember, this is a very thin film. So even if I etch away some of it, the change in topography is not very drastic. So I'm not really able to see much on there. Again, the amplitude, the raw data, we're not going to worry about that. But when I look at the phase, I can definitely see areas that were etched away, these bright areas, and then the surrounding PVP. So practically invisible on topography, but with phase, now we can pick up these material properties on the sample surface that we would otherwise not be able to see. And let me go ahead and bring it back to the microscope because it hit something big on here. So again, we're hitting some feature on here. So you can kind of, again, tell that difference between what topography looks like and what phase looks like. I think it looks like it just might be some PVP that got kind of piled up. So if I am on an area of interest, I can start manipulating some of my parameters. For example, if I wanted to clear this up some, that's when I could start going into slowing down my probe. And if you notice, that scan speed just slowed down. So now my tip is going to be able to get into the corners and pick up a better resolution. I don't want to change my points per line while it's running, and that's because it'll lock up this system. So I'm not going to do that one. And then, of course, I can always play with my set point. But if you notice, this box underneath my topography, this is our trace retrace. So we can visualize, I think of it as a real-time cross-sectional analysis. So our black line is our positive X direction of this scan. So black line is it moving to the right, or white line is it moving to the left. Ideally, we want to get these as close to superimposed as we can. We're not going to be able to get it completely superimposed, but we can get close. I can always play with these gains to try to clear that up. I'll just show you a quick example. Let's say I just hit 2200, so that's what we'll try. So you can see if I move it to 2200, that's not very smooth. That's going to give us, well, actually a horrible image. So I can adjust these gains and manipulate that to smooth this out. And actually you can hopefully be able to see, especially on this amplitude, we have a lot of noises coming in. That's not really part of the sample. So we want to eliminate that while keeping our resolution and smooth this out. And to do that, I just simply start lowering it. Change the I first and then the P to match. And it got a little better. And I just continue to do that until I get to something satisfactory. So even at 1000, I brought it down here. It's still a little jagged here. I can still see a little bit of noise. So I want to continue to lower that until I've eliminated all that. So now the noise is gone, or looks like it's gone. It's hard for me to see. It's a small screen. This is nice and smooth, close to superimposed. At this point, I would have an optimized image. Now I could slow down my scan rate even more if I wanted to. And anytime that you make a change, you might need to slightly adjust these gains. But if I were to say, this is the image that I want, then I could just simply stop and restart it. The reason why I would want to do that is because I don't want to capture an image that has all my adjustments on it. And then I could have a quote unquote pristine image. Any questions on operation? And I do apologize that I was not able to find that scanned area. I just simply did not have enough time, and I've had a little bit of technical difficulty this morning, so I do apologize for that. Or if anyone would like to take the controls just to play with some of these parameters and see what it does.
I add one quick thing. Phase is sometimes the most one of the better options to image nanoscale patterns added or deposited using AFM lithography, because remember, phase imaging is a subset of tapping mode, and tapping mode is a gentler imaging approach. Remember, when we image with lateral force microscopy, we're in contact mode. So the tip is making direct contact with the sample surface. So let's say, for instance, we deposit some bacterial cells or some biomolecule on the sample surface using DPN. If we try to image that with lateral force microscopy and friction in contact mode, then we're likely to shred through that material. So phase imaging gives us a more gentler approach when imaging nanoscale structures deposited using LFM lithography, especially patterns deposited using thin films or biological molecules.
Did a great job. We appreciate it. Thank you very much.
Real quick, Bob, I see Greg just put in a question. He wants to know how susceptible the AFM is to nearby movements. A person walking by a nearby truck or a loud noise. It's very susceptible to vibration. As a matter of fact, why not try this here real quick. Let me share this with you again, and I might be able to show you an example. So I think you guys can see the microscope. So I'm just going to smack my desk. And you notice there was a lot of vibration that showed up on the trace retrace. And it's also now going to show up in my image as those little streaks. The microscopes that we have in the lab, they're actually held on a granite stage by bungee cords to help with that vibration. And I'll let Wes comment on the prices.
Does anyone have any questions on pricing? Yes, they are expensive, but Nanosurf has a lot of educational discounts for educators. So if you're interested in obtaining specific pricing for specific AFMs for a specific application, I can get you in contact with the service engineer that who works for Nanosurf, who we do our business through.
Thank you.